In this video, I'm going to give an explanation for this chart that appeared in the New York Times a few days ago. What it shows is a variety of diseases, everything from measles and chickenpox, bird flu, the Spanish flu, that's the pandemic flu from 1918. Um, and I'm going to show you a little bit about this new coronavirus. Now, since this chart was made, there's been some additional information. I'm going to tell you a little bit about what uh, what has changed. So first of all, to explain what do the axes mean? The vertical scale is the fatality rate. And if you'll notice, this is a logarithmic scale. That means that from this unit to this unit is a factor of 10, and from this unit to this unit is a factor of 10, and from here to here is a factor of 10. So, for example, seasonal flu says that only 0.1% of patients die, whereas for the bird flu up here, you can see that's closer to 50%. Ebola is also very high, MERS is very high, smallpox is very high, but then the common cold and then an ordinary flu season like this one from 2009, it may be that very few people die, and so those diseases appear way down here. The coronavirus is probably somewhere between 2 and 5%. So this block is really a little bit lower perhaps than it should be. Maybe it should be up here. Again, more data will have to be collected, and of course a lot depends on the available medical care. But anyway, that's what this first axis means. It's logarithmic to kind of spread things out and to show you, for example, that the Spanish flu is over 10 times more deadly than the seasonal flu because it's more than one unit up here. MERS is about 10 times as deadly as the Spanish flu because you can see it's about a unit here above the Spanish flu. So that's the vertical axis. The horizontal axis is actually a concept from epidemiology, and I'm going to explain that in terms of differential equations. The axis is labeled average number of people infected by each sick person. That's the basic reproductive ratio for the disease. I'm going to now switch over to Mathematica and show you what that means. Okay, this is a calculation called an SIR model, and you'll see why it's called that. It dates back to a paper by Kermack and McKendrick in the early part of the 20th century. It divides the population into three compartments. These are the susceptible, the infected, and the recovered or removed. The names associated with these variables kind of change depending on the context and what's known about the disease. Since I'm doing this in Mathematica and you can sometimes get into trouble using single letters for variable names, I'm going to call these SUS for susceptible, INF for infected, and REC for recovered. Susceptible individuals have no immunity, infected individuals actually have the disease, and recovered individuals have recovered from the disease and are presumed to be immune. There are some complications with the COVID-19 disease. There are some reports that I think are not well understood, indicating that someone could catch the disease again. It's not known whether that's a testing error or whether there's maybe a second strain going around. I don't have a good answer for that yet, but for this model, I'm going to simply assume that individuals who have recovered from the disease are immune. Since this is happening on a time scale of just a few months, changes to the population size are negligible. There will be some births and deaths, but not significant enough to really change the dynamics that we're looking at. So for the purposes of this model, the total population is going to remain constant. Okay, so here's the dynamics. We're going to set up these differential equations, and I'll do it in 2 steps. Individuals move from the susceptible compartment to the infected compartment at a rate proportional to the number of susceptible and the number of infected individuals. A way to see this is to imagine that each individual comes into contact with m others on average. A fraction INF over n total of those are infected, and then there's some probability p of transmitting the infection at each contact. So that gives this differential equation that the rate of change of the number of susceptibles is that we lose susceptible people at a rate proportional to how many are already there, and then this is the rate, and right here is the fact that this rate changes with the number of infected people. To conserve the total population, the same term appears but added in the differential equation for the number of infected individuals. That's the infection process. To complete the equations, we need to have a recovery process. So suppose that individuals recover from the infected state and enter the recovered compartment at some rate, which I'll call rRec. So that means that just at any given time, this fraction of infected individuals recover. They're subtracted from the infected compartment and added to the recovered compartment. And just to keep things simple, I'm going to define rInf to be an infection rate that's going to replace everything here except for the INF of t, which brings us to these differential equations in Mathematica notation. And let me evaluate those. So you can see here the susceptibles are moved to the infected compartment, and infected people eventually move to the recovered compartment. Now, it's not really possible to get exact symbolic solutions to this, and it probably wouldn't be useful to have those anyway. Instead, what we're interested in is the overall shape of the epidemic, just what happens to the number of infected individuals. What we're seeing in the COVID-19 case is exponential growth in the number of cases. I'm going to focus on the United States because that's where we are, and show you how I've set this up. So initially, there's essentially nobody is recovered and nobody's infected. So what you're seeing for the infected is the number of susceptibles times this constant rInf. Since the number of susceptibles is pretty much the whole population to begin with, for small values of time, the number of infected individuals will grow approximately exponentially. So that's as if this term is not there and if the SUS of t is constant. Now here's where I fit this to some information that I got from the web. The population of the United States right now is roughly 330 million. So let's enter that. Now I found a website called worldometers.info, which lists a lot of information, a lot of numbers. And in particular, when I was working on this the other day, there were 200 active cases in the US on March 5th, and there were 23,729 on March 21st. So let me show you where that came from. So here's my web browser. This is the Worldometer, and if you go down here, there's several charts. What I'm looking for is active cases, and this was the number that I used for March 21st, and there's March 5th. And you can see that they've added a few new points since then, but the trend is roughly the same. Now, what I've done here is to put in an estimate for rInf. The way you get this is to set up exponential growth like what you see up here, and to plug in that on March 5th, which is day 0, there should be 200 infected people. At time 16, which is March 21st, there are 23,729. You then solve for rInf times in total, and this is the result. And then you can divide by pop_us to get rInf_est by itself. Okay, so there we go. That number by itself is kind of hard to interpret. Let me just show you a few things here. So for one thing, this confirms that on day 16, according to this simple exponential model, there are 23,729. Now, exponential growth has a property called doubling time. Earlier estimates for the doubling time of COVID-19 were that it doubles every 4 days. Let me show you what happens if I run the calculation with these numbers. I get 2.32 days. What that means, let me go back to the worldometer. What that means is that every 2.3 days, the number of infected cases doubles. So for example, here on March 19th, let's say it's about 13,400. 2 and a fraction days later, there will be 26,900 something. And you can see that's really not too far off. The reason I say that's bleak is that if it doubles every 2.3 days, then, well, after 10 doubling periods, the number of cases will be multiplied by 1,024, which means that if we've got, say, tens of thousands of cases now, in 23 days, we'll have tens of millions. It's likely that the exponential growth will break down before then. I certainly hope it does. But I don't have information indicating that at this time. I do need to make a modification to rInf_est for the SIR dynamics. That's because the exponential model that I've just showed you ignores the recovery process. And at the very beginning, the recovery process is negligible. But once you get about a month in, you really need to have a recovery process. So these are the values of rInf and rRec that I'm going to use in the next calculation. The reason for rRec is it's 1/14 because at the moment the estimates that I'm getting for recovery time out of the literature are about 2 weeks. It seems to vary a lot, that some people have a very mild case and it doesn't last all that long. Other people have pneumonia and they're in the hospital for several weeks. I don't have precise data on the average time, but a ballpark estimate that I've seen in several different places is 2 weeks. So that means that as the epidemic gets going, on any given day, approximately 1/14 of the population will be recovered on that day. I'll say there's some more complications with this number, and I'll get to that later. But this at least gives us something that we can calculate with that'll give us something reasonable. Okay. So for the numerics, I'm going to use the Mathematica function ndsolve. That's the numerical differential equation solver. Here's how this works. I'm going to use join to take the differential equations and join them to these initial conditions. Again, I'm going to say that on day 0, which was March 5th, there were 200 infected people. The slash dot notation here is how you do a substitution in Mathematica. So I'm going to use these numbers, and this is the notation that replaces rInf and rRec in my differential equations with these specific numbers. ND-solve will give me a susceptible population, an infected population, and a recovered population, and I'm going to let it run for 1 year. So time goes from 0 days to 365 days. I've wrapped the whole thing in first because solve functions in Mathematica always return a list of possible solutions. For ND-solve, there's only ever one solution, but to be consistent with other solving tools in Mathematica, it does return a list of that one item, and so the first just pulls out that one item. Now, once I've run this, you can see there brief pictures. I'm going to show you this plot. It's hard to see, but there are actually two curves here. This shows that the number of infected individuals based on that numerical solution lines up very closely to the simple exponential model that I had used based on the data from the Worldometer website. And they align so well that they're practically indistinguishable. And again, what I did to get this was to fiddle with this factor right here until I got the two curves to line up. And again, one thing that is scary about this is that after 30 days, we're seeing an infected population around 1 million, which will be around April 5th, according to the calendar that I've used in this model. And just as a couple of checks, there's the initial condition, 200 infected individuals at time 0, around 23,000 infected individuals on day 16, which was March 21st. Here's what a year looks like. That's a linear scale vertically and a full year. And if we zoom in a little bit, this is the initial increase. And you can see that around April 1st, it's looking like around 500,000. So then what do we make of that peak in the epidemic, the hump? So this is just the first 100 days or so, so that's about 3 months. So you can see that the peak occurs about 60 days in, so that would be around May 5th. And that number is, well, let me run the actual calculation here. That number is 1.6 times 10 to the 8th at day 53. 1.6 times 10 to the 8th is 160 million, which is half the country. That's half the country sick at the same time. And if that happens, well, things are going to be bad. Now, I should point out that hope is not lost. Here's why that's just going to be really, really bad. If we assume that 2% of cases develop into pneumonia and need to be hospitalized, that means that at that peak, at the 160 million people infected on day 53, it means that we'll have 3.2 million people in the hospital all at the same time, which is more than 3 times the total number of hospital beds in the United States. So we want to avoid this. To give you some hope that this is possible, I'll show this in a minute, but China managed to get their infection to get under control. So they leveled out at about 80,000 total cases when I last checked. That's the idea behind flattening the curve. Here's how this works. Here's what this looks like in this SIR model. We reduce the number of people that come into contact each other. That effectively reduces rInf. So remember, rInf, as I had defined it way up here, let me see if I can find it again. You can think of rInf as being, I overshot, come on, as being that each individual comes into contact with M others, and a fraction of those are infected. So remember, rInf is all of this except for the inf of T. Right here. What the social distancing does is to reduce that M. So after doing some experimenting, here's something very hopeful. Suppose that we can cut contacts by a factor of 6, so that each individual only has 1/6 as many contacts as in an unregulated society. That decreases rInf by a factor of 6, and I can run the same thing. At this point, I'm going to say from the condition of, let me go ahead and update this number. Currently on March 23rd, which was yesterday actually, the number was 42,886. So let's put that in, 42,886. And now let's run the calculation. Now the infection is going to die out, and you'll see that when I run this. So there's no hump at all. The infection dies out. It takes about a year for it to really disappear into the bottom of the graph, but which is a lot longer than I think any of us would like to see. But this is a lot better than having 3.2 million people in the hospital all at the same time in a matter of a couple of months. Now, just to show how delicate this is, suppose that we can only achieve a factor of 4 reduction. There will still be a peak if we can get that factor of 4 reduction. But you can see that the peak is almost a year out. And yeah, let me go ahead and fix this calculation as well. What is it, 43,880? 43,880. Oh, I got to look it up again. 886. 43,886. Let me run this again, just so that my numbers are consistent. At this point, the peak is at around 9 million sick, and 2% of 9 million is only 180,000, and that's much preferred to 3.2 million sick at the same time. It's still kind of depressing because this is, you can see right here, this is a year from right now. The advantage, though, is that if we can slow things down at this point, the researchers that are working on the vaccine may have had a chance to get a working vaccine. Getting a vaccine, getting a candidate for a vaccine, I think, is not going to take too long. I think there are already some in the works. However, they have to be tested for effectiveness. They also have to be tested for safety, and it may be that the early vaccines are not effective or not safe, at which point they'll have to keep working on them. And then there's the problem of mass production. The flu vaccine has to be prepared months in advance. Traditionally, it's been grown in eggs, and viruses are just funny. They thrive under the specific conditions that they're sort of tuned for, and outside of those conditions, they tend to die rather quickly. So it's hard to breed a virus and then to extract just the crucial part of its encasement and then form a vaccine out of that. The way a vaccine works is that it consists of just the proteins on the outer shell that trigger an immune response. And so this is sometimes difficult to get right. So what have I done here, and what's the big difference between a factor of 6 and a factor of 4? Well, let me start by calling up the derivative of the number of infected individuals. And you can see right here, I've evaluated it and just plugged in times 0 just to be definite. And there's this factor that's appeared here. In epidemiology literature, the basic reproduction number or basic reproduction ratio is defined to be, in the notation I've used here, rInf times in total over rRec. What that means is that at time 0, inf prime is r0 minus 1 times rRec times inf 0. If we can make this number negative, then inf will actually decrease. The number of infections will decrease, and the epidemic will die out. However, if r0 is greater than 1, then initially the number of infected individuals will grow because the derivative of inf is positive, and that's what leads to a peak in the epidemic. If you work it out, rInf and rRec are dimensionless, and in total is a population count, so the units of r0 are population count. What this number means is at the beginning of the epidemic, each individual spreads the disease to r0 susceptible individuals on average. So in the previous bunch of calculations, I had estimated rInf and rRec. Here is what happens if you calculate r0. You get 5.18. Let me go back to the New York Times diagram. The number here on this horizontal axis is r0. That's the basic reproduction number. The diagram was drawn when the basic reproduction number was estimated to be between, looks like about 2 and 5. Well, yeah, right here, between 2 and 4. It looks like that was a low estimate. It looks like that the dot for the COVID-19 virus should go around here. So around 5 for R0 and somewhere between 2% and 5% on the fatality rate. This makes it kind of a perfect storm of a disease. You can see here some other diseases that have been in the news. Ebola is very deadly, but it requires very close contact to transmit. You have to transmit it from, say, blood to blood. Other respiratory diseases, SARS and MERS, are also not all that easy to transmit, even though they do have a higher fatality rate. And the bird flu is also one of these. It looks like the bird flu can be transmitted from birds to humans, but not from humans to humans, which is why the bird flu is here with an R0 of exactly 0. On the other extreme, we have something like measles that is extremely contagious, but very few people die, and most of the fatalities from measles are very young children, babies. And then nobody really dies of chickenpox. But this area right here where it looks like COVID-19 is, it's something that's rather contagious, rather high R0, and with a significant fraction of complications. Um, Pneumonia in the case of COVID-19. So we want to modify this so that it's less than 1, which means that we need to cut the contact rate, the rInf, by a factor of at least 5.2. And that boundary of 5.18 to 5.2, that's really the very precise boundary between this behavior, which was with a factor of 4, and, oh, where did it go? This behavior with a factor of 6 reduction. This is why we really need to stay on the ball, do the social distancing, and this is why colleges are closed. This is why sporting events are being canceled. It's just to try to reduce the number of contacts between individuals as much as possible. Now let me mention a few of the weaknesses. I won't read all of this. One of the complications with COVID-19 is that it seems to have a long incubation period. So that's when someone has the virus and is able to spread it, but isn't experiencing symptoms. So they may not know that they're infected. Another complication is that there may be a lot of cases that are going misdiagnosed. For example, if someone has low fever and a sore throat and a cough, they might be diagnosed with the flu or with a bad cold and be out for a few days and not even realize that they had the COVID-19 virus. So it means that there are some issues with the numbers that I've used to generate this. Like I said, I've used numbers that were reported to this data conglomeration site on the web, but there could be some significant changes. I know that there have been several times that a testing center cleared a backlog or testing improved and there was a sudden change in the number of known cases. So things like that can change these numbers dramatically. Also, like I said, the 14-day recovery period is just kind of a rough guess based on what I've heard. One problem with that is that people can apparently continue to spread the virus even after their symptoms have subsided. But also, when you have a cough, sometimes the irritation in your throat continues long after the disease itself has run its course, and it just takes a while for the irritation to be healed. So it's possible that the 14-day recovery period is not a good estimate if people are able to pass the disease on after they've seemingly recovered, then the 14 days is too short. But if people are recovering and no longer contagious but still coughing, then maybe the 14 days is too long. I don't really know. I do have this calculation that I can show you. So this is with the original solution without social distancing. And what I'm seeing there is that on day 17, which would have been March 22nd, according to the model, the number of cases should be around 7,600, but the Worldometer only estimated 178 recovered cases. Part of that may be that people are not being reported as being recovered. A recovery is not nearly as newsworthy as an infection, so there may be just a reporting bias there, but again, I don't really know. Let me go back to the Worldometer and show you something that is kind of concerning. So this that you're seeing right here is the number of active cases, the number of infected people. Unfortunately, it doesn't have this option. This is the total number of cases. So it's the sum of the infected cases and the recovered cases. I can put this on a logarithmic scale, and you can see that from March 2nd up until March 23rd, on a logarithmic scale vertically, this looks really clean. This is a nice straight line, and it means that the disease is still experiencing exponential growth. That means that we're still on the way up the hill toward the peak of the epidemic. That's not a good sign. We want to turn that around. Now, let me go up here to the top and switch to China. So again, this is the total number of cases recorded in China. This jump was due to an improvement in the testing procedure. And you can see here that there was exponential growth for a while, and then the Chinese, by imposing quarantines and social distancing, were able to stop the total number of cases from increasing. This is effectively the integral of the rInf function from the model, and I didn't plot that in the previous calculations. But you can see they leveled out supposedly at around 80,000, 81,000. So there is hope that in the United States we will be able to do that as well, but we've got to be vigilant about the social distancing. This is also a nice chart to have. This is the number of new cases reported per day. Again, this is a fluke because some improvement was made to the testing and reporting procedure right about that time. And here you can see the number of infected people. Again, there's a problem with the reporting, but you can see that it has the shape of an epidemic from the SIR model, but luckily it stopped at about 60,000 people, 58,000 people infected all at once. So there is hope. Also, the number of deaths levels off, of course. China reports 3,277 on March 23rd out of total number of cases. Let's get that number, 81,171. And that's a 4% fatality rate, which is actually more bleak than the 2% that I'd used in my Mathematica calculations. So this is a serious epidemic. I mean, it does seem sort of crazy to bring the country to a halt over what amounts to a bad cold, but it spreads like a cold, and enough people develop deadly pneumonia from it that it's really important to stop it. So I think I will stop there. There you go. That's the SIR model applied to the ongoing COVID-19 pandemic.